All right, so we're going to do a roller coaster problem. This is similar to a roller coaster problem that you guys did last week, where you, on your homework, should have determined how fast it was moving at the top of a second and third hill. But what changes here is now we have the roller coaster going through a loop. And what we want to do is we want to find the maximum safe height that somebody would be able to stay inside of the roller coaster without requiring a safety harness. Sure, they'll have one, but we want to make sure that it's safe even if that safety harness failed. So for that to be true, let's look at the free body diagram at the top of the loop. At the top of the loop, there's some different possibilities. We know that the force of gravity has to be acting downward, but depending on how we do this loop, depending on our speed, our normal force will be different. If the loop is really, really fast, and this is an inverted loop, so you can be upside down here, like the roller coaster would be there. If we went really fast, you guys can imagine that you'd be like crushed down into your seat, and that normal force would be pushing you down. If, on the other hand, we were going very, very slow, that's where we would have to have the safety harness, and then the safety harness would be pushing us up, keeping us from falling out. But if we went at the minimum safe speed, the speed at which like you can make it through the loop without feeling any forces acting on you, if we did it in that case, there would be no normal force acting on you. So that's what we're going for. We're going for that speed at which the force of gravity is the only one acting on you, and we don't need normal force either pushing you down or holding you up. So based on that, let's set up some forces equations. We can say that the acceleration would be the sum of the forces over the mass. And in this problem, we want it to only be mg, the only force. So mass cancels. The acceleration equals g. We could go one step further. Since this is circular motion, we could substitute in v squared over r equals g, and then transform this into an equation for the minimum velocity being g times r square rooted. So that's the slowest we could go without falling out of the roller coaster or without requiring a harness. So with that speed now understood, let's do this from an energy perspective. We're starting from this point here, I'm going to call that E1, and we're getting to this point here, E2. So from E1 to E2, the energy has to be the same. And at E1, we know we have only gravitational potential energy. But at E2, oops, I didn't mean to write that. At E2, we would have some gravitational potential because we're at the top of this loop, plus some kinetic energy. This is going to be mgh1, and then ug. This is going to be mg, and then we actually have to think about this for a sec. What is the height here? The height of this is going to be equal to 2 times the radius, because that's how far the loop would be off the ground. So I'm going to put in a 2 times r right there, plus 1/2 mv squared. But the velocity that we're going to use there is the square root of gr, because that's the minimum speed. That's what we already know. We have to at least be at that speed to stay in the roller coaster. So if I plug that in real fast, let's notice mass is going to cancel. So I'll just go gh1 equals g2r plus 1/2, and then square root of gr squared would just be gr. And so notice, oh look, g is also canceling. So actually, this probably doesn't even, this roller coaster, once we build it, doesn't even have to be done on Earth. If they can make it through the loop on Earth, they could do it on in any other circumstance. It would still function. All right, so simplifying this, we get h1 equals 2r plus 1/2 r. And if you combine those, 2r would be the same thing as 4/2. So 4/2 plus 1/2 would be 5/2 r. So whatever the height is at the beginning, the radius will be, the height has to be 5/2 radii, or the radii at this point here would have to be 2/5 the original height in order for us to make it through this loop. So that is our final answer. Big takeaways, again, are understanding why I had to do this calculation, and then some of the work that was done along the energy calculation of why I plugged in the numbers that I plugged in and then how to solve it. So thank you for watching. I hope this helps you guys understand these kind of problems in the future.